Okay, in this lecture, we will learn about the telescopes and some optical characteristics of telescope and design of telescope and mounting system variations, and also that actually even among the more commonly used reflective telescope nowadays, there are many variations and because of the different focus design. So we will learn about the types of telescope in this lecture, followed by some special observing techniques that actually developed over the past about 2 or 3 decades. Okay? So first, the telescope mounting system. So this is actually very closely related to the coordinate system that actually we learned about the last time. So first one is the telescope is mounted so that actually that the two tilting angle, so two guide the angles that actually they determine the pointing of the telescope is following exactly the concept of the alt azimuth, the coordinate system. So in such a way that actually the one angle is just controlling the altitude of the telescope pointing, and the other one is azimuth. So this type of mounting system is known as alt azimuth or horizontal mounting system. So this is simple. So that actually the most of the hobby type of small the reflective and refractive telescope were actually mounted on this alt azimuth, the mounting system historically. But the problem was actually a challenging way in the past was the tracking the celestial object over long duration of observation because of the diurnal the motion of the celestial object on this azimuth angle. The mounting system is complicated. So it is the nonlinear complex sinusoidal, the trigonometric, the functions that actually need to follow so that actually to keep an object within the field of view of the telescope, one need to actually adjust this declination and then the azimuth angle in a very complicated way. So in a simple mechanical way, it was very difficult. So therefore, that actually the more popular, the easier to control type of mounting telescope mounting system was they developed, which is very similar. Or in the I think in the concept, it is the same as the equatorial coordinate system. So in there, the two angles that actually that determines the telescope pointing is declination and right ascension. So that means actually the telescope mounting pole that is actually holding the telescope tube need to be pointed and then aligned perfectly with the Earth's rotational axis, meaning that actually it is aligned parallel to the celestial the North Pole and the South Pole. In the northern hemisphere, this pole need to actually point very accurately to the North Pole. If that is the case, then all this celestial object diurnal motion is only following along the one angle, so which is right ascension, the angle. So that means declination is fixed, and all you need to do to keep the object within the field of view, you just they control the angle, following or adjusting the angle only in the one element, which is the right ascension. It's known as also our angle direction. So because of this reason, that actually equatorial the mounting system was popular because it allows the long duration of the tracked observation. Okay? But as the telescope getting larger and larger, this equatorial mounting system requires very delicate the balance, weight balance of the telescope. So this actually getting, I think, as the telescope is getting larger and even larger than 4 meter, 6 meter telescope, it becomes nearly impossible to actually make this equatorial system work perfectly. Because of the weight balancing issue of the telescope, and also the further the challenge was this equatorial mounting system requires the larger the dome for the given the same size of the telescope. So with the advent of the computer controlled the tracking system, now that actually that larger telescope, especially the 8 meters or the larger telescope system mounting system, is actually going back to the alt azimuth, the mounting system. Okay. Then let's talk about some optical characteristics of the telescope. First, easiest one that actually determine the primary, the one single important number that actually determine the telescope mostly is the size. How do we actually determine the size or specify the size of the telescope? It's the size of the largest optical the element, which is the entrance first optical element that actually that the light rays that actually from the celestial object they meet with the telescope. So that is the objective the optical element, and that objective for the refractive telescope is the objective lens, and for the reflective telescope is the objective mirror, the reflective primary mirror. The size of that the objective the lens or mirror is defined as the aperture of the telescope, and this aperture size determines the two important parameters. One is setting the diffraction limit, which affect the image quality of the telescope, theoretical maximum, the limit of the imaging capability for the given the size of the telescope, and another one is actually just gathering power. Light gathering power is simply proportional to the area of the optical the objective optical element. Then the second the important parameter of the telescope is the focal length of the objective the element. Okay, so how far away that actually the focus is from the center of that optical element. In the case of the reflective the mirror, that the focus measured in physical lengths, that actually how far away from the center of this optical the mirror to that actual focus. So this the focal length actually determines several interesting and then also the important the parameters, such as field of view. Field of view is basically inversely proportional to the focal length. So that means actually the larger the focal length, you actually you zoom in into the particular area of the sky. So that actually that the actual the obtained field of view is proportional to the detector size, meaning that actually in the focal plane all these the light rays actually just focused and then re-imaged, so they're actually creating the re-imaged focal plane. At that focal plane, how large that actually the detector size that actually you are using is affecting the final field of view. So for the given the detector size f0, field of view is inversely proportional to the focal length of the primary the mirror. So field of view is f0 over f. Okay, so and the open times that are actually not in professional the astronomical the telescope, but for the typical the hobby the telescope that actually the amateur the astronomers actually purchase from like the from internet or maybe Walmart or not. Oftentimes actually people just focus on the magnification. So the magnification is a good parameter to choose, but oftentimes for the real celestial, the in-depth, rigorous, the astronomical observation, magnification is actually hardly matter. Okay? Because most of the objects are actually so far away, very small, and magnification can be changed by altering the eyepiece, as you will see later on. Okay, so final magnification is the focal length of the primary mirror divided by focal length of the eyepiece. So for the given telescope, that the focal length of the primary mirror is not changeable, so it is fixed. But by changing the different the size eyepiece, you can actually adjust the magnification of the observation. So oftentimes for the hobby, the telescope, astronomical telescope, oftentimes there is a series of different lengths of eyepiece actually comes in. So when you actually just want to use the higher magnification, you use the short, the version of the eyepiece. Okay? But a professional the astronomer, the professional level of the telescope, this magnification is actually hardly matter, but more the related to the diffraction limit, and also that actually this detector size. So how many pixels actually are they available in a given detector size? So sampling size, pixel size, and so on are actually more important. Then app number oftentimes actually used, especially in like the photography, the astronomical, the photography, and that is actually basically this, the focal length of the primary mirror divided by aperture size. Okay? And angular resolution is actually just one of the important parameters. Oftentimes actually they denote it as a theta measured in usually arcsecond. Okay? And the mathematically the demonstrable that actually for the given size the given aperture size of the telescope, that angular the resolution, which is actually in the diffraction limit of the angular resolution of the theoretically perfect telescope, is limited by this parameter, 1.22 times wavelength of the observation divided by size of the telescope. Okay? So for the given wavelengths, larger the telescope, that actually providing the smaller the diffraction limit, meaning that actually you can create more crispy and sharper images. So, and also that actually this wavelength dependency is actually important, because for the optical wavelengths, say that actually the lambda is something like the 0.5 micron, that's the optical wavelengths, versus say that actually that mid-infrared observation. Mid-infrared observation maybe about 10 micron is a typical nominal, it's the center of the mid-infrared, the range. So that means even for the same telescope, observing at the optical versus observing with the same telescope, which is actually not possible, as we will see later on. If the same size telescope observed in optical wavelengths versus mid-infrared, the imaging observation, even using the same telescope, is 20 times worse. Okay, 20 times worse than the optical wavelengths. So that, which means that actually to create the same crispy high angular resolution imaging and at long wavelengths, you need to actually use the larger telescope. So that is actually that makes that actually the more reason that actually that the longer wavelengths the observation is more challenged, and then special type of telescope design or observing technique need to be developed. And at later lectures we will actually just focus on these long wavelengths specialized observation later on. Okay. Then let's get back to the more fundamental the difference. Okay? So there are two by design. There are actually two very distinct the telescope design. One is using the mirror as the primary or the objective element. That's the reflective the telescope, versus objective lens. Okay? So in that case is a refractive telescope. Traditionally, refractive telescope has been used first, but the refractive telescope, when you actually try to build the larger and larger telescope, because the lens is actually getting larger and the lens becomes really heavy, right? So that rapidly increasing mass is the main limiting the parameter, and then great challenge to create really big refractive telescope, and also that actually that the reflective telescope requires long tube. long telescope tube. So for the given the aperture size of the telescope, it requires really heavy, the massive element of the materials and long tube, and also actually because of this long tube and then heavy weight, by pointing different the part of the sky, this telescope tube is actually sagging, and then the image quality is actually becoming compromised. So practical limit of the good quality refracted telescope was about 1 or 2 meter the size of the telescope. For the really large telescope greater than 2 meter in size are using the reflected mirror as the primary the objective element. So the compared to the lens that actually that to make the perfect image, you need actually the materials inside of the lens need to be uniform, and also the both sides entering and then exiting side of the surface need to be perfect. But the compared to this lens, the more the restrictive requirement for the good quality, good imaging quality, the mirror need to be actually just polished perfectly only on one side, and then it doesn't care that actually what is actually behind the reflective the surface. So only the reflecting surface need to be perfectly smoothed, and that compared to the lens, that actually that the refractive the refraction is actually a function of the wavelength, so that actually the focus the measured, I think the focus achieved by given the lens are actually different for different wavelengths. So meaning that actually when you put the screen on the fixed distance away from a single the glass, the lens, you can actually see that actually that at particular distance only one wavelength is perfectly focused, and then other wavelengths are actually just making us unfocused surrounding rings. This is actually known as the chromatic aberration. So lens are actually producing by nature they're actually chromatic aberration, while they're actually reflective, the telescope doesn't. Okay? And the reflected telescope it is because as we will see later on, it is shorter in telescope tube, and as the less the massive, so lighter compared to the same size refracted telescope, so it is easier to mount. Okay? So because of these reasons, that actually that the nowadays actually even for the hobby, the telescope, the reflective telescope basically just the took over, and the nearly the almost all the professional telescope are actually all designed and then manufactured as the reflective telescope nowadays. And let's talk about the aberration a little more. Okay, so there are three main the aberration in telescope. One is spherical aberration. Imagine that actually this is the primary mirror. That's the reflective the surface. Okay, so think about the optics. If the reflecting surface is parabola, okay, and then that's the axis of the parabolic surface, okay, and then that's the focus. Then all parallel incoming light to this the optical axis are actually focused into a single the location. That's the focus of the parabolic the reflecting surface. Okay, so no matter that actually whether it's far away off axis, the light parallel to the optical axis versus very close to the center of the mirror, all focused in a single point. That's the parabolic the mirror, right? But parabolic mirror is actually difficult to manufacture. So when you actually just they make a grinding stones that actually making the perfect the surface for the primary mirror, spherical mirror is much easier to manufacture. Okay? Then spherical mirror actually has a built-in limitation in such a way that actually far that away the parallel light actually from the far off-axis light is actually focused onto the certain the position on the optical axis, whereas actually that the light that actually close to the optical axis focused on a different location. So that means actually that at a given, if you actually put a screen or detector in one location, you can actually, for the spherical aberrations, actually making that the center is this near to the center of the mirror is actually it is well focused, but outside is blurry, unfocused. You need actually special the corrective the optics lens, or that's some combination of the special type of lens is needed to correct this spherical aberration. Second most common is actually coma. This is actually the image of the coma. One side is actually the high well focused beam, but actually has long the tail. This is a telltale sign of misaligned the optical element. Okay, then more the commonly appeared nowadays in the high level the high quality imaging observation is astigmatism. Okay, so this is similar to the coma, but actually that intensity is more like uniform, and this is mainly deformed by the imperfect surface of the optical element, such as like the lenses and various the prisms and then reflected mirrors, and then when that actually surface is actually deviated from the perfectly smoothed surface, then you actually create lots of the non-uniform the aberrations that actually through the whole combination of this imperfect the surface. Okay? So the minimizing these type of aberrations and then creating the perfect no aberrations, but actually perfectly the diffraction limited the observation, the creating the perfect the diffraction patterns of the point source is the sign of the really highly tuned and well maintained the telescope. Okay. And then let's talk about the focal plane of the telescope. So for the simplest the design of the telescope, you have only one the reflective the primary mirror, and that's the telescope tube. All this parallel the incoming light are actually focused into the single the point. This the focus formed by the primary mirror is called prime focus. Okay, and prime focus is actually usually they provide the largest field of view for that given telescope, and because it used the only one mirror, right, one optical element, which is the primary mirror, its image quality is only affected by the imperfection of the single optical element, which is the primary mirror. So usually that actually the prime focus is providing two really good advantages as the largest field of view, then least the number of the optical surface that actually involved, indicating that actually they're providing the chance that actually being the best image quality. So that the prime focus has been used as the main imaging the mode. I think they putting the instrument in that at that prime focus, such as actually like this prime focus cage. So in the old days, for the large telescope, at the location of the prime focus, there is an observer cage that actually that at the prime focus range, there is the observer is actually putting in the photographic plate and then taking the pictures and whatnot in the at night. And I heard that actually the horrible story is that actually that the wintertime observation on at this prime cage, the wind was actually blowing and then it's getting deadly cold, and then you need to actually go to the restroom, but actually that go to the restroom you need to actually just lower the telescope and then taking down the letters and when, so that in the old days, about 40, 50, 60 years ago, the prime focus imaging in a prime focus case has been challenging. Okay? But still, that actually the most radio telescope nowadays actually still utilizing the prime focus system, such as like this Arecibo, right? So that's the main reflected mirror of the radio telescope Arecibo, and then that's the the location of the secondary mirror usually, but actually that's the prime focus. Okay, and the one of the supporting cable was actually just broken recently, so that actually the surface of this primary the mirror of the Arecibo got actually damaged recently. So I heard that actually that they the fundraising to repair that damage. Right? Then let's just get to more details about the traditional design of the reflective telescope. So the Newtonian the prime focus is actually is advantageous because it actually they provide the largest field of view and then also that best image quality, but because it is sitting in front inside of the tube, accessing that prime focus is very inconvenient. So that actually the famous Isaac Newton, that actually he in his the telescope design, he actually put a tilted mirror close to the entrance of the telescope tube and brought that actually the focus out of the telescope tube, so that actually you can actually put eyepiece here, then the observer can actually really see without really obstructing the primary mirrors or just telescope tube. So this Newtonian telescope has been actually really good in invention and used a lot of the early days of the reflective telescope. Then in some cases that actually that there was a need to increase the focal length of the main mirror. It's mainly that actually try to increase the magnification so that actually that solar system objects such as like the planets or not or surface of the planet can be they studied in great details, so that actually that special type of actually long tube design that actually trying in an effort to increase the focal length. That type of the focus design is called the Gregorian. Then it's similar to the Gregorian, but actually that now they're actually using the secondary mirror, okay, in front of the prime focus. Then the backside, the central region of the primary mirror has a hole, so that actually the focused beam can be actually brought outside of the telescope tube. Then instrument or eyepiece can be actually attached on the backside. So this design is called Cassegrain, and most of the modern day the hobby telescope are actually using this Cassegrain the focus design. And later that actually, as you will see later on, even the world-class largest telescope is actually the utilizing this Cassegrain focus system as well. Okay, so let's look a little more. I think the different design as well. So that's I think we already saw this prime focus, Newtonian focus, okay, and Cassegrain focus that actually we already talked about. Another the type of for the nice design is actually some variation of the Cassegrain and the Newtonian. So that actually using the secondary mirror in front and that actually the tertiary mirror, the actually tilted mirror that actually bring out the focus out of the telescope tube, such as this Newtonian, but actually is close to the primary mirror. And this location is usually that's the support axis of the telescope tube. So that focus is actually being brought out from the surface axis of the telescope tube, and this has actually the surprisingly very convenient the usage, and then also they provide the advantage for the modern day large telescope, as you will see more I think specifics about the later slide. Another type that actually used quite a lot and then frequently that actually in the past was Coude design. It is actually using that actually the multiple mirrors, secondary mirror and then tilted tertiary mirror, and then that actually it bring they focus out of the telescope tube in a long the chain by using multiple fourth meter and then fifth meters whatnot. And this is actually basically that's the telescope tube, right? And the primary mirror is here, and secondary mirror, tertiary mirror is there. Then the focus is actually brought out into the supporting axis. And then there's a fourth mirror is actually sending the beam in there. And then finally the fifth mirror is actually sending the beam into the instrument that is stationed far away from the telescope. Oftentimes they're actually in a separate room, so that the really delicate the instruments such as high precision radial velocity, the ECL spectrograph, which is actually prone to the very tiny the vibrations and whatnot. So that actually that telescope pointing or the tracking motors whatnot can actually cause the vibration and then affect the precision of the measurement. Because of this, CUDA focus has been used for the specialized spectroscopic observation, the type of telescope, which actually provide the highest chance of actually getting the high precision radial velocity measurement. Okay, so this particular the telescope is the 1 meter telescope on the Canary Island in Spain. Okay, so this is actually one of the few remaining CUDA focused telescope nowadays. What is the current modern day the telescope design? Okay, that is actually combinations of the Nasmyth focus and Cassegrain focus. So this is the most of the modern day the telescopes such as like 8 meter class to 10 meter class telescope are actually all utilizing this type. So it is the Nasmyth plus Cassegrain focus system. Okay, why this is actually useful? Because 8 meter class or larger telescope are actually really heavy, so that actually it is mounted on the alt-azimuth or the mounting system, and the support axis of the alt-azimuth, which is actually this axis, right? This axis is actually used in a way that actually that primary mirror and then the tertiary mirror is actually bring out the Nasmyth focus on either side of the supporting axis. Okay, so by using the rotating the tilted mirror, okay, and a tilted tertiary mirror, you can actually send the Nasmyth focus either on the right side or on the left side. Why it is actually good, beneficial for us? Because they brought out the focus can be on the telescope floor level or away from the telescope mounting. So that means actually really heavy instrument can be mounted and then utilized in the Nasmyth focus on the telescope, the observatory, the floor level. Okay, and because you have two Nasmyth foci, by rotating this tertiary mirror, you can actually choose either right side the Nasmyth focus or left side. Typically use they designate it as the Nasmyth focus A or B. So by rotating this single mirror, you can choose either instrument A on the A focus or on the B focus. At the same time, that actually by removing this rotating tertiary mirror, you can actually obtain the Cassegrain focus as well, utilize Cassegrain focus as well. So by the allowing that actually they're rotating this tilted mirror or taking it out from the optical the chain, you can utilize three focus systems, three foci at the same time, two Nasmyth focus or one Cassegrain focus. Oftentimes that actually on the Cassegrain focus, there is an instrument attachment that actually the platform that actually being attached, and then also that actually it has the rotating mirrors as well, so that actually the up to 4 or 5 instrument can be chosen with simply just rotating the tilted telescope, a tilted mirror, or just taking it out. So in theory, that actually you can have at least 3 the instrument. It's ready to be used by selecting and the tilted tertiary mirror, and by adding typically more, such as like the Gemini 8-meter class telescope, there's a Cossack ray instrument, the selector, which is actually also the utilizing the rotating the mirror, tilted mirror. They're actually allowing up to 5 instruments attached at the same time. So in a given time, any given time, there are actually 5 to about 7 instruments can be selected at any given time. Okay, so changing observing instrument is actually snap, maybe just a minute. 1 minute is actually enough to really the switching from one instrument to another instrument. This is actually a drastic the improvement from the earlier day, because in the earlier day, say that actually switching from the simple imaging observation to the spectroscopic observation, you need to actually just call the telescope engineers, and then he comes in and then just changing the mirrors and then changing from imaging mode or switching the instrument. That oftentimes actually take like 1 hour or 2 hours. That's why there is in the old days that many telescope actually just didn't allow the instrument the switch in the middle of the night. So oftentimes actually that actually has been, they had limited the scientific the flexibility. So one it's open more often than not that actually the observers actually the making a on the fly the real time decision that they after taking the picture, and he or she realized that, oh, this is so interesting, potentially groundbreaking discovery. I need to actually take the spectrum. In the old days, they couldn't do, but nowadays actually because of the so easy the instrument the switch, that can be actually done very easily. Let's talk about the telescope mirrors before we actually wrap up the part of the lecture. Telescope mirror is actually made of the special type of glass, and this glass are actually so-called special materials actually made of so-called zero door. Okay, so this is actually that the practice of zero means has the zero thermal expansion. So this special type of the glass material actually does not actually really easily expand or shrink because of the temperature fluctuation. So that actually is the metal, the casing of this primary mirror versus this glass actually have very similar the thermal expansion rate. So that actually they increase and then shrink they at the almost similar level, even in a very really tiny bit compared to the typical glass. So that actually this geodur, the special glass materials are actually being used for the primary mirror manufacturing. Then this geodur is actually slightly denser than typical the glass. That actually is really heavy. Okay, so this is the 8-meter the primary mirror of the 8-meter the Gemini telescope, and look at that actually that look at the thickness, the height of this the mirror. This is actually getting really heavy. Okay, so that actually to reduce the weight, that actually on the back side of the primary mirror is actually just carved out. So that actually is like the honeycomb of the design to reduce the weight. Still, that actually the final honeycomb design is actually very heavy, but still compared to the monolithic single, the mirror is actually much lighter. Okay, then final the surface of the really well smoothed surface of the primary mirror need to be coated with some reflective materials. In the old days, that actually the aluminum was actually used as the coating of the material. This aluminum actually reflect 98.7% of the incoming optical light, meaning that actually 1.3% is absorbed, right? compared to that, the silver is actually even shinier. So that actually it reflects 99.5% of the incoming reflected light, meaning that actually only 0.5% of the incident light is observed. This reflectivity, high reflectivity, is actually not only that actually is important, but actually also that actually is more so becoming important for the long wavelengths observation, because emissivity, which means actually that how much of energy that actually that the mirror is actually emit at certain wavelengths, is 1 minus reflectivity. So say that actually in the previous example, silver and then aluminum, let's compare to this case. If it is actually coated at the aluminum, then aluminum's reflectivity is 0.987. So that means 0.13 is the emissivity, meaning that actually that the aluminum coated mirror is actually just emit the about 3 times, I think roughly about 3 times stronger than the silver coated the primary mirror. This is actually especially important in the mid-infrared long wavelengths, that actually where that the temperature of this telescope mirror is actually emit primarily at the peak, the wavelengths of roughly about 10 micron. So at 10 micron, that the using the highest reflectivity the material is actually important to reduce the emissivity, so that actually telescope does not actually produce any noisy the photons at that wavelengths. So silver is actually better, but actually, as you know, that actually once the silver is exposed to the open air, then it reacts with the oxygens, and then it actually getting tainted, and then getting darker, producing the oxidated the silver compound, which actually lose reflectivity greatly. So has to be a special type of the protective layer for the silver coated the primary mirror, and this is the image taken by the Gemini Observatory that actually just who pioneered of this silver coating in the mid 2000. Okay? So nowadays, actually, most of the infrared specific the telescopes are actually using this silver the coating as the main reflective material. Okay? So this wraps up the telescope designs and then different types of the telescope focus and different mounting systems or not. So in the next slide, we will actually talk about something that actually affecting the imaging quality of the telescope. Okay? So we will talk about the seeing and the atmosphere effect and then diffraction limit.